Hi everyone, I am Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 3-1, Force Vibration of Undamped Single Degree of Freedom Structure. In the previous lecture, this is lecture 2, we have already studied free vibration of undamped single degree of freedom structure. Free vibration is induced by initial conditions, such as initial displacement or initial velocity. And force vibration is induced by external forces, such as earthquakes, typhoon. But earthquake and typhoon are so irregular, are so random. Therefore, the response under these forces are so complicated. In this lecture, we focus on simple forces, such as unit step force, unit impulse force, and unit sinusoidal force. Here are some terminologies. The first one, single degree of freedom. If a structure has only one degree of freedom, that means that the structure can be described by only one displacement variable. And in Chinese, 单自由度. Undamped, that means that there's no damping for the structure. In Chinese, 无阻尼. Force vibration, that's the vibration induced by external forces. In Chinese, 强迫振动. Inertial force, that's the force generated by the mass and the acceleration. In Chinese, 惯性力. Restoring force, that's the force generated by the stiffness of the structure and the displacement of the structure. In Chinese, 回复力. External force, that's the force applied to the structure. In Chinese, 外力. Unit step response, that's the structural response under unit step forces. In Chinese, 单位部接反应. Unit impulse response, that's the structural responses under unit impulse force. In Chinese, 单位脉冲反应. Unit sinusoidal response, that's the structural responses under unit sinusoidal force. In Chinese, 单位间歇反应. For a single degree of freedom, it can be modeled by mass and spring. M is the mass of the structure, and K is the stiffness of the structure. And Ft here is the external force applied to the structure. And because it's a single degree of freedom, the displacement of structure can be represented by only one variable, xt. If the structure moves to the right-hand side with displacement xt, and the restoring force will point to the left, kxt, and the external force is assumed to be positive, therefore it's pointing to the right. And from Newton's second law, we have mat equal to ft. Ft is positive because it's pointing to the right. Minus kxt. Kxt is negative because it points to the left. And at is the second derivative of displacement. Therefore, we have mx double dot equal to ft minus kxt. If we move minus kxt from the right-hand side of the equation to the left-hand side of the equation, then we have mx double dot plus kxt equal to f. And this is the motion equation of the structure. From engineering mathematics, this equation can be considered as second order because the highest derivative is second order. Non-homogeneous because the forcing function is non-zero with constant coefficients because the mass m and stiffness K are constants. They do not vary with time. From the first term is inertial force, mx double dot. The second term here is restoring force, kxt. And the term on the right-hand side of the equation is external force, Ft. Therefore, the motion equation can be considered as dynamic equilibrium equation of a single degree of freedom structure. First of all, we consider unit step response. Before solving for unit step response, we consider unit step function first. And unit step function, when t is negative, the unit step function ut is 0. When t is positive, the unit step function is equal to 1. And at t equal to 0, there's a jump from 0 to 1 because the height of the step is a unit. Therefore, it's called unit step function. If the external force is assigned to be a unit step force, therefore we have Ft equal to ut. If we substitute the external force into the motion equation, we have mx double dot plus kx equal to Ft equal to ut. If we are only interested for the time duration that is larger than 0, therefore the unit step force to be a constant. And this equation can be solved by ordinary differential equation. And here are two initial conditions. One is initial displacement, x of 0 equal to 0. Another is initial velocity, x dot of 0 equal to 0. Since this equation is non-homogeneous, therefore the solution for this non-homogeneous ordinary differential equation has two parts. One part is homogeneous solution, mx double dot plus kx equal to 0. There's no external force. And then we solve this equation. We can find out the homogeneous solution, xh equal to c1 cosine omega 0t plus c2 sine omega 0t. Another part of the equation is particular solution. Since the forcing function is a constant, from the method of undetermined coefficient, we can assign the particular solution equal to A. Therefore, xpt equal to A. And A can be solved by the method of undetermined coefficient. And take the first derivative. We have xp dot equal to 0. Take the derivative again. We have xp double dot equal to 0. And we substitute xp into the differential equation and xp double dot into the differential equation. Then we have m times 0 plus ka equal to 1. Then we can solve for a equal to 1 divided by ka. Once we have solved for a, then we can substitute a back to the particular solution. Then we can have the particular solution and the homogeneous solution. And we combine the particular solution with the homogeneous solution. It gives the general solution. xt equal to xh plus xp equal to c1 cosine omega 0t plus c2 sine omega 0t plus 1 divided by k. And this is the general solution for the displacement. And c1, c2 are two coefficients of integration. They can be found by the two initial conditions. One is initial displacement, the other is initial velocity. If we take the first derivative to the displacement, we can have the velocity equal to minus c1 omega 0 sine omega 0t plus c2 omega 0 cosine omega 0t. From the initial displacement, x of 0 equal to 0, c1 times cosine 0 equal to 1 plus c2 times sine 0 equal to 0 plus 1 divided by k equal to 0. Then from this equation, we can solve for C1 equal to minus 1 divided by K. And here is initial velocity, x dot of 0 equal to 0. Minus C1 omega 0, sine 0 equal to 0, plus C2 omega 0, cosine 0 equal to 1 equal to 0. And from this equation, we can solve for C2 equal to 0. Once we have the coefficient of integration C1 and C2, and we substitute C1 and C2 back to the displacement function, then we can solve for structural displacement xt equal to 1 divided by k times 1 minus cosine omega 0t. And from the structural displacement, it can be observed that the displacement vibrates at the frequency of omega 0. That's the structural frequency. But it does not vibrate above 0. It vibrates above 1 divided by k. When t equal to 0, xt equal to 1 divided by k, 1 minus 1, because cosine 0 equal to 1. And then we have x equal to 0. Therefore, this equation satisfies the initial condition. If the force is applied very, very slowly to the structure, then the acceleration becomes 0. Then we have kx equal to 1, and then we can solve for x equal to 1 divided by k. Because the force is applied very, very slowly, and this displacement is called static displacement. And then we consider the displacement function again. If cosine omega 0t equal to minus 1, that means that when omega 0t equal to pi, then x of t equal to 1 minus minus 1 equal to 2 divided by k. Therefore, this is the maximum dynamic displacement. From the maximum dynamic displacement and the static displacement, it's very easy to find out that maximum dynamic displacement is 2 times the static displacement. Therefore, under static force, the displacement is less. Under dynamic force, the displacement is larger. It can be called the dynamic effect of the force. Therefore, the structural displacement vibrates at a frequency omega 0, but it does not vibrate above 0. It vibrates above 1 divided by k. That is the static displacement. Therefore, the structural displacement vibrates about the static displacement between 0 and the maximum dynamic displacement, 2 divided by k. After studying the unit step response, we go to the unit impulse response. And here is the unit impulse function. When t is non-zero, delta t equal to 0. When t equal to 0, delta t tends to infinity. But the area under this function equal to 1. Therefore, the integration from 0 minus to 0 plus delta t dt equal to 1. Because the area under this function, under this curve equal to 1, therefore is a unit. And is an impulse function. So that the function here is called unit impulse function. 0 minus, that means that it's very close to 0, but very close to the left of the 0. And 0 plus is a little bit to the right of the time t equal to 0. If we assign the external force to be delta t, the unit impulse function, and then we substitute to the motion equation, we can have mx double dot plus kx equal to ft equal to delta t. And here are two initial conditions. Initial displacement equal to 0, initial velocity equal to 0. Since delta t, when t equal to 0, delta t tends to infinity. Therefore, we cannot handle the equation directly. Therefore, we integrate the equation from 0 minus to 0 plus Let us consider the term on the right-hand side of the equation, integrating from 0 minus to 0 plus delta t dt equal to 1 according to the definition of unit impulse function. And then we consider the second term on the left-hand side of the equation. Since it is impossible to generate considerable displacement without spending any time, therefore the displacement function in general is continuous. Therefore, at the time 0 minus, because it's very close to 0, therefore x of 0 minus equal to x of 0. And also x of 0 plus equal to x of 0, also equal to 0. Therefore, in the range between 0 minus to 0 plus, xt equal to x0, x of 0 equal to 0. Therefore, this integration, because the integrand equal to 0, this integration equal to 0, this term vanishes. And then we consider the first term on the left-hand side of the equation. You integrate x double dot dt. After integration, it becomes x dot. The integration of acceleration becomes the velocity. Therefore, we have two terms, x dot of 0 plus minus x dot of 0 minus. Because when t is negative, there's no external force, and the initial velocity equal to 0. Therefore, x dot of 0 minus equal to 0. Only x dot of 0 plus left. Therefore, from this equation, we can have mx dot of 0 plus equal to 1. Then we can solve for x dot of 0 positive equal to 1 divided by m. If we consider the term larger than 0, therefore, when t is non-zero, the delta function equal to 0. Therefore, the forcing function here equal to 0. We have mx double dot plus kxt, kx equal to 0. Therefore, it becomes a free vibration problem. And here are two initial conditions. X of 0 plus equal to x of 0 equal to 0 because of the continuity of displacement function. X dot of 0 plus equal to 1 divided by m. Therefore, we have two initial conditions. It's a free vibration problem. From the result of the previous lecture, this is lecture 2, we can solve xt. Xt is the unit impulse displacement response equal to x0 dot divided by omega 0 sine omega 0 t. Because x0 dot equal to 1 divided by m. Therefore, the displacement equal to 1 divided by m omega 0 sine omega 0 t. Therefore, the displacement vibrates at the natural frequency. That's the structural frequency omega 0. And here are two functions. One is a unit step function. The other is unit impulse function. Let us differentiate the unit step function with respect to t. When t is negative, ut equal to 0. Because ut is constant. Therefore, the differentiation equal to 0. When t is positive, ut equal to 1 is a constant. Is constant. Therefore, the differentiation equal to 0. When t equal to 0, there's a jump from 0 to 1. Therefore, the slope here tends to infinity. Therefore, the differentiation of ut at t equal to 0 tends to infinity. And the integration, the area under this curve equal to 1. Therefore, it becomes unit impulse function. Finally, we have the differentiation of ut with respect to t equal to delta t. Therefore, we have the differentiation of unit step function becomes unit impulse function. And then we consider the response under unit step force and under unit impulse force. from the previous results, we can have the unit step response xut equal to 1 divided by k times 1 minus cosine omega 0t. And the unit impulse response x delta t equal to 1 divided by m omega 0, sine omega 0t. Now we differentiate the unit step response with respect to t. Then we have dt 1 divided by k times 1 minus cosine omega 0 t. Then we have omega 0 divided by k sine omega 0 t, because k equal to m omega 0, and omega 0 is cancelled out. Therefore, we have 1 divided by m omega 0 sine omega 0 t, and this solution is the same as the unit impulse response. Therefore, we have the differentiation of unit step response equal to unit impulse response. Finally, we have the result that if ut is if the differentiation of ut equal to delta t, therefore the response under unit step force, the differentiation of this response equal to unit impulse response. And third, we consider unit sinusoidal response, and the forcing function is sine omega t. Omega is the excitation frequency. 1 is the amplitude of the excitation. Therefore, it's called unit because of the amplitude, unit amplitude. Sinusoidal because it's a sine function. Therefore, it's called unit sinusoidal function. If the external force is assigned to be unit sinusoidal function, ft equal to sine omega t, and we are only interested for the term larger than 0. Then we substitute this external force into the equation of motion. We have mx double dot plus kx equal to sine omega t. And omega is the excitation frequency. It is different from the structural frequency omega 0. And here are two initial conditions. Initial displacement equal to 0. Initial velocity equal to 0. And because this ordinary differential equation is non-homogeneous, therefore the solution to this equation consists of two parts. One is homogeneous solution, the other is particular solution. For the homogeneous solution, we assign the forcing function equal to 0. Therefore, we have mx double dot plus kx equal to 0. After solving this differential equation, we can have the homogeneous solution xh equal to c1 cosine omega 0 t plus c2 sine omega 0 t. And then we consider the particular solution. There's another part of the solution of the non-homogeneous ordinary differential equation. Because the forcing function here is a sine omega t, from the method of undetermined coefficient, xpt, the particular solution, can be expressed as a cosine omega t plus b sine omega t. A and b are coefficients to be determined by the method of undetermined coefficient. Take the first derivative. We have xp dot equal to minus a omega sine omega t plus b omega cosine omega t. Take the derivative again. We have xp double dot equal to minus a omega square cosine omega t minus b omega square sine omega t. And we substitute xpt into the differential equation, xp double dot into the differential equation. Therefore, we have minus m omega square times a cosine omega t plus b sine omega t plus m omega square times b a cosine omega t plus b sine omega t equal to sine omega t. Because cosine omega t and sine omega t are independent, therefore when the equality holds, the coefficient on the left-hand side of the equation for cosine omega t equal to that on the right-hand side of the equation. Therefore, we have m times omega 0 square minus omega square times a equal to 0, because there's no cosine omega t here, or we can say that the coefficient for cosine omega t equal to 0. Then we can solve for a equal to 0. And then we consider sine omega t. This one is the coefficient on the left-hand side of the equation, and 1 is the coefficient on the right-hand side of the equation. And from this equality, we can solve for b equal to 1 divided by m omega square minus omega square. Once we solve for a and b, we substitute back to the particular solution. We can have xp equal to 1 divided by m times omega 0 square minus omega square sine omega t. Let us observe the homogeneous solution. Xh equal to c1 cosine omega 0 t plus c2 sine omega 0 t. Therefore, for this part of the displacement, it vibrates at structural frequency omega 0. And then we observe the particular solution. Xpt equal to 1 divided by m times omega 0 square minus omega square times sine omega t. Therefore, for this part of the displacement, it vibrates at excitation frequency omega. Once we have the particular solution and the homogeneous solution, we combine these two, we can have the general solution for the displacement equal to c1 cosine omega 0 t plus c2 sine omega 0 t plus 1 divided by m times omega 0 square minus omega square times sine omega t. For the first two terms, it vibrates at structural frequency omega 0. For the third term, it vibrates at excitation frequency omega. Therefore, the displacement vibrates at two frequencies. One is structural frequency omega 0. The other is excitation frequency omega. And C1, C2 are two coefficients of integration. And from the initial displacement and initial velocity, we can solve for C1 and C2. When we take the derivative for the displacement, we can have the velocity equal to minus C1 omega 0 sine omega 0 t plus C2 omega 0 cosine omega 0 t plus omega cosine omega t divided by m times omega 0 square minus omega square. From the initial displacement, x of 0 equal to 0. C1 times cosine 0 equal to 1 plus C2 times sine 0 equal to 0 plus sine 0 equal to 0 equal to 0. And from this equation, we can solve for C1 equal to 0 and then consider the initial velocity. X star of 0 equal to 0. We have minus C1 omega 0 times sine 0 equal to 0 plus C2 omega 0 cosine 0 equal to 1 plus omega times cosine 0 equal to 1 divided by m times omega 0 square minus omega square equal to 0. And from this equation, we can solve for C2 equal to minus omega divided by m omega 0 times omega 0 square minus omega square. Once we solve for C1 and C2, we substitute these two coefficients back to the displacement function. Then we can have the structural displacement xt equal to minus omega divided by m omega 0 times omega 0 square minus omega square sine omega 0 t plus 1 divided by m times omega 0 square minus omega square times sine omega t. From the first term of the displacement, it vibrates at structural frequency omega 0. from the second term of the displacement if I base at the excitation frequency omega. When omega tends to 0, the amplitude here disappears. When omega tends to 0, the amplitude for the excitation frequency equal to 1 divided by m omega square equal to 1 divided by k, and is called static displacement. When omega tends to 0, therefore the excitation frequency is very, very low. Therefore the force is applied very slowly to the structure. Therefore the displacement amplitude equal to the static displacement. When omega tends to omega 0, that means that the excitation approaching to the structural frequency. The excitation frequency is approaching to the structural frequency. And the denominator here tends to 0. The denominator here tends to 0. Therefore, the amplitude becomes infinity. And under this case, resonance happens, and it oscillates and diverges. When omega tends to infinity, the amplitude here becomes very, very small. The amplitude here becomes very, very small. Therefore, the amplitude of the displacement tends to 0. Now, if we change the excitation frequency to be equal to the structural frequency, and in this case, the excitation frequency is the same as the structural frequency. Therefore, we have mx double dot plus kx equal to psi omega t, omega equal to omega 0. And here are two initial conditions: initial displacement equal to 0, initial velocity equal to 0. Because this equation is non-homogeneous ordinary differential equation, the solution for the motion equation has two parts. One is homogeneous solution. Then we assign the forcing function equal to 0. We have mx double dot plus kx equal to 0. After solving this homogeneous differential equation, we have the homogeneous solution, xh equal to c1 cosine omega 0 t plus c2 sine omega 0 t. Now we have the homogeneous solution. Then we are going to find out the particular solution. Even though the forcing part is sine omega t and omega equal to omega 0, but we cannot assign the particular solution to be a cosine omega 0 t plus b sine omega 0 t. In this way, the particular solution will be the same as the homogeneous solution. We cannot solve for the particular solution. Therefore, there's a change here. We assign t cosine omega 0 t and t sine omega 0 t instead of cosine omega 0 t and sine omega 0 t. And a and b here are coefficients to be determined, and they can be determined by the method of undetermined coefficients. Take the first derivative. We have xp dot, something in this way, and take the derivative again. We have xp double dot, expressed in this way, and substitute xp into the differential equation, substitute xp dot into differential equation. Then we have this equality. Because cosine omega 0 t and sine omega 0 t are independent, therefore this equality holds if and only if the coefficient of cosine omega 0 t on the left hand side of the equation equal to the right hand side of the equation. From the same argument, the coefficient of sine omega 0 t on the left hand side of the equation equal to that on the right hand side of the equation. So that we can have two equations, one for sine omega 0 t. Here is the coefficient on the left hand side of the equation equal to the coefficient on the right hand side of the equation. And from this equation, we can solve for a equal to minus 1 divided by 2m omega 0. And here is the coefficient for cosine omega 0 t on the left hand side of the equation, and 0 here is the coefficient of cosine omega 0 t on the right hand side of the equation. And from this equation, we can solve for b equal to 0. Once a and b are solved, we substitute back to the particular solution. Then we can solve for the particular solution. From the homogeneous solution, xh equal to c1 cosine omega 0t plus c2 sine omega 0t. Therefore, for this part of the displacement, it vibrates at the structural frequency omega 0. Since c1 and c2 are constant, therefore the amplitude of the vibration is also constant. Then we move to the particular solution. xp equal to minus t divided by 2m omega 0 cosine omega 0t. For this part of the displacement, it also vibrates at the structural frequency omega 0. But let us observe the amplitude here. The amplitude increases with time. That means that when t tends to infinity, the amplitude of the displacement also tends to infinity. From the homogeneous solution and the particular solution, we combine these two together, we can have the general solution equal to c1 cosine omega 0t plus c2 sine omega 0t minus t divided by 2m omega 0 cosine omega 0t. Therefore, the displacement vibrates at only one frequency. That's the structural frequency omega 0, and omega 0, because the excitation frequency omega is the same as the structural frequency omega 0. And C1 and C2 here are two coefficients of integration. From the initial displacement and initial velocity, these two conditions, we can solve for C1 and C2. Take the first derivative of the displacement. We have the velocity expressed in this way. And from initial displacement, x of 0 equal to 0. Then we have c1 times cosine 0 equal to 1 plus c2 times sine 0 equal to 0 minus t equal to 0 equal to 0. From this equation, we can solve for c1 equal to 0. From the initial velocity, x dot of 0 equal to 0. Then we have minus c1 omega 0 sine 0 equal to 0 plus c2 omega 0 cosine 0 equal to 1 plus 0 minus 1 divided by 2m omega 0 equal to 0. We solve for this equation, and then we have c2 equal to 1 divided by 2m omega 0 square. Once we have the coefficients c1 and c2, we substitute back to the displacement function. We can have the structural displacement x equal to 1 divided by 2m omega 0 square sine omega 0 t minus 1 divided by 2m omega 0 t cosine omega 0 t. Therefore, the displacement vibrates at the structural frequency omega 0, omega 0. From the first term, the amplitude of the vibration is constant. But from the second term, the amplitude of the vibration increases with time. As t tends to infinity, the amplitude of the displacement also tends to infinity. And here's the displacement. As the excitation frequency omega equal to the structural frequency omega 0, resonance happens, and the response oscillates and diverges, and the amplitude of the vibration increases with time. As t tends to infinity, the amplitude of the displacement also tends to infinity. Therefore, the structure is unstable. And here are some references. The first reference is the Seismic Design Codes of Building in Taiwan. It's written in Chinese. It's published in 2011 by the Ministry of Interior. You can download this Seismic Design Code from this website. The other reference is ordinary differential equation. It can be found out from any textbook on engineering mathematics. And here are some videos. There's a video for lecture 2-1. Here is the English version, and here's the Chinese version. And that's the video for lecture 2-2. And here's the English version, and here's the Chinese version. And the video of lecture 3.1 is the current video, is under construction. But the Chinese version has already been uploaded to this website. And the video for lecture 3-2 is under construction, but the Chinese version has already been uploaded to this website. And the video for lecture 4, here's the English version, and here's the Chinese version. And in this lecture, we focus on force vibration of undamped structure. By solving the differential equation, we can find out the unit step response under unit step function. We can find out the unit impulse response under unit impulse force. And then we can also solve for unit sinusoidal response under unit sinusoidal force. That's all for this lecture. Thank you. See you next time. Bye bye.